Hello viewers, continuing in the series of videos covering the key concepts in the chapter on electric charges and fields. In this particular today's video, we will discuss about Coulomb's law and Coulomb's law in vector form. If you want to see more such videos, hit the subscribe button and like and share the video. Coulomb's law. What is Coulomb's law? Let us talk about the statement of Coulomb's law. If two stationary and point charges whose spatial, what is a point charge? Whose size is very small as compared to other distances. The two charges are Q1, Q2. This is Q1 and this is Q2. They are separated both by a distance r from each other. Then the force of attraction or repulsion between them is directly proportional to the product of the two charges. Okay, so the force of attraction or repulsion between them is directly proportional to the product of the two charges, that is F is proportional to Q1, Q2, and inversely proportional to the square of the distance between the two charges, inversely proportional to the square of the distance between the two charges. According to the statement, the relation which we get is F is proportional to Q1, Q2 upon R square. In order to remove the proportionality sign, we introduce a constant K, and this constant K is F is equal to K Q1 Q2 upon R square. So we get F is equal to K Q1 Q2 upon R square, and this K is called the electrostatic force constant, as is mentioned on the slide over here. Right, it is called electrostatic force constant. The value of this K depends upon the nature of the medium separating the two charges and the system of units. So what is the nature of the medium separating the two charges? The value of K depends on it, and also which system of units we are talking about, whether it's a SI system of units or CGS system of units. These are the two major system of units which we talk about. Now, in SI system of units, when the two charges are in free space, then the value of this K is equal to 1 upon 4 pi epsilon naught. That means the value of this K is written as 1 upon 4 pi epsilon naught. This epsilon naught is called absolute electrical permittivity of free space. Epsilon naught is called absolute electrical permittivity of free space, which means that how much electricity can pass through the free space. That is the meaning of electrical permittivity of free space. Okay, so K is equal to 1 upon 4 pi epsilon naught, and the numerical value of K is equal to 9 into 10 to the power of 9 Newton meter square upon Coulomb square, as is mentioned on the slide over here also. 9 into 10 to the power of 9 Newton meter square upon Coulomb square. That is the value of K. Right, now the value and dimensions of epsilon naught. Now, as the value of K is 9 into 10 to the power of 9, which is equal to 1 upon 4 pi epsilon naught, we can also find out what is the numerical value of epsilon naught, which can be found out, and it is equal to 8.85 into 10 to the power of minus 12, and the units of epsilon naught will be inverse of the units of your value, inverse of the units of K, that is electrostatic force constant. So it will be Coulomb square Newton inverse meter minus 2. Okay, so those will be the units of epsilon naught. Now the dimensions of epsilon naught are m minus 1, L minus 3, T4, A2. I will show you how you can derive, how you can find out the dimensions of this epsilon naught. In the just in 2 minutes I will show you that. And in CGS system of units, the value of K is equal to 1 when the charges are in free space. So in a CGS system, the value of K is equal to 1 in CGS system of units, and in SI system of units, the value of K is equal to 1 upon 4 pi epsilon naught, which is equal to 9 into 10 to the power of 9 Newton meter square upon Coulomb square. This is in SI system of units. Okay. Now as I told you, I will show you how you can get the dimensions of epsilon naught. So let's find out the dimensions of epsilon naught. Epsilon naught. We want to find out the dimensions. We know k is equal to 1 upon 4 pi epsilon naught, and you know that f is equal to k into q1 q2 upon r square. So what is k equal to over here? K is equal to f into r square upon q1 into q2. Right, that is equal to this f into r square upon q1 into q2, and k is equal to 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught is equal to f into r square upon q1 into q2. Right, this is what it is. So basically, what are we trying to find out? We are trying to find out what is the dimensions of epsilon naught. So epsilon naught will be equal to, we can find out the dimensions of epsilon naught from here, and also as I told you that epsilon naught is equal to, the units of epsilon naught are Coulomb square upon Newton meter square. Right. So you can do it from here also, because from here also epsilon naught, because 1 upon 4 pi will not have any dimensions. So epsilon naught will be equal to nothing but it will be equal to q1 q2 upon f into r square. q1 q2 upon f into r square. Right, that will be your epsilon naught. 1 upon 4 pi will not have any dimensions. So we can write that down. As you know that charge upon time is equal to current. Current is measured in ampere. Time is measured in terms of seconds, and which in dimensions we write it down as t. So basically charge in the charge dimensions are a into t. Okay, so we will write it down and find out exactly what it is. So this is equal to Coulomb square, which is equal to AT, again AT because it's square, Coulomb square, upon Newton, which is the unit of force, and the force can be written as ml t minus 2, and also this is meter square, which is L2. Okay, so this whole thing can be written as m minus 1 L minus 3 t minus 2. When it goes to the numerator, it will become t4, and again it will become a2. Right, so this is your these are the dimensions of your epsilon naught. As you can see on the slide also over here, m minus 1 L minus 3 T4 A2, these are the dimensions of epsilon naught. Right. Okay, so you've understood the dimensions of epsilon naught, how we have got them down, derived them. No need to remember, but we can derive it. Now let's talk about Coulomb's law in vector form. Okay, now for the Coulomb's law in vector form, as you can see over here, we have taken a coordinate axis. O is the origin, and we have the two coordinates, one is OX and the other is OY. Right, and the two charges are at the positions A and B. Okay, so the two charges Q1 and Q2, they are at the positions A and B. Okay, now the position vector of the charge Q1 is R1 vector, and the position vector of the charge Q2 is R2 vector. R2 vector. Right, this is R1 vector and this is R2 vector. Now the force F12, right, the force F vector 1 2 or F vector 1 2, let me write it here. This is the force on the charge Q1 due to the charge Q2, and F21 vector, that is this one, F21 vector, it is the force on the charge Q2 due to the charge Q1. Now when we are talking about the force on the charge Q2, due to the charge q1, we will be talking about the unit vector which is directed from q1 to q2, and when we talk about the force on the charge q1 due to q2, we will be talking about the unit vector directed from q2 to q1. So that is r cap 21, okay, that will be our unit vector 21 and the other will be our unit vector 12. So here in vector form, Coulomb's law may be expressed as F21 vector. This is the force on charge q2 due to q1, which can be written as 1 upon 4 pi epsilon naught, which is the value of k, q1 q2 upon r square into r12 cap. Why? Because we are talking about the force on q2 due to the charge q1, and therefore we will be talking about the unit vector directed from q1 to q2, right? So this unit vector directed from q1 to q2 is r cap 12. And what is r cap 12? In 11th standard we have learnt about the unit vectors, and the definition of unit vector is the vector upon the magnitude of the vector, that is r12 vector upon r. It is the unit vector in the direction from q1 to q2. Similarly, F12 vector, it can be written as force on charge q1 due to q2. And now we will be talking about, in this case we will take the unit vector directed from q2 to q1, that is 1 upon 4 pi epsilon naught q1 q2 upon r square r21 cap, and where r21 cap is r21 vector upon r, that is the unit vector in the direction from q2 to q1. So if we take this, as you can see that the two unit vectors are directing in the opposite directions, the forces F12 vector is equal to minus of F21 vector. As you can see, the force F12 vector is equal to minus of F21 vector, as you can see, okay. Also, the Coulombian forces between unlike charges. What do you mean by unlike charges? Here the unlike charges means that the two charges, one is positive, one is negative. Then q1 q2, the product of q1 and q2 charges will always be less than 0, because a positive and a negative charge, if plus q1 and this is minus q1, if plus q1 you are talking about and minus q1, then q1 q2 will be less than 0. And if q1 q2 will be less than 0, that means the two charges are equal and opposite. There will be a force of attraction between the two charges, and the force of attraction between the two charges, in this case it can be shown in this particular manner as shown in the diagram, that is F12 vector and equal, which is equal to F12 vector is in this direction and F21 vector will be in the opposite direction, right. So here you can see that the two forces are equal, the two charges are equal and opposite, and hence the forces will be attractive forces. Thank you everyone. If you have any doubts, you can write down in the comment section, and also any other clarification required, you can do so in the comment section.